Chapter 6 basically is just a review of a whole bunch of trig. The basic trig stuff. Chapter 7, we get more into the not so basic trig stuff, and then we're going to take a test in hopefully a week and a half, maybe 2 weeks over trig stuff. So this book opts to use the unit circle approach to trigonometry as opposed to the right triangle, where you do SOHCAHTOA. If you have no idea what I'm talking about, Google it on YouTube. There's lots of great videos out there. There's lots of corny videos out there on trig. The cornier typically the better. But there's a lot of resources available online for trig. Don't let just my lecture be the only thing that you can, consult whenever you're studying or boning up on trig. We start with the unit circle. Remember that the equation of a circle centered at 0, 0 with a radius of 1 is going to be x squared plus y squared equals 1. This is the equation that would give us the graph of the unit circle. It's just a circle centered at 0, 0 with a radius of 1. This book takes this straight angle, or this straight line t, to be equal to s. S is a variable that we reserve for the arc length. So if I were to curve this red line around this circle, what I would end up with is the arc length here. It just so happens, and this book does not mention it for several pages, that this angle right here that's cut out is an angle theta measured in radians. It also corresponds to t. Some books refer to that angle right there as t. Some refer to them as theta. As you can see, this book is going to refer to it as t. On a unit circle, we can take any point on the circle. It can be represented by a set of ordered pairs. The x value of that point is cosine of t. The y value, by definition, is sine t. So that's where these values came from. Let t be a real number and p be a point on the unit circle. Then sine t is going to be y. Well, what they're doing, if you remember your right triangle trigonometry, is they took this point on the unit circle. They dropped a perpendicular line. There's a right triangle. This is a value that corresponds to x right here. So that distance right there is x. This distance right here is y. And the radius is 1. So using right triangle trig, if you want to take that right angle out of there, if this is your angle theta, and then this is the adjacent side, the opposite side of the angle, and the radius, we have our right triangle property. Sine is opposite, which is y, over hypotenuse, which is 1. Y over 1 is y. Do you see the correlation between the right triangle trig and the unit circle? Now, I'm explaining this as if you've had some trig before somewhere in your life. Is there anybody who has never had trigonometry? Okay, I'm counting on you two to ask lots of questions. Okay, let's start a little more basic than what I just started. These are functions: sine, cosine, tangent, secant, and cotangent. They're functions kind of like square root is a function, log is a function. These are, though, called trig functions. When we put an angle into a function, t here represents this angle, we get a numerical value out. The sine of that angle is going to correspond to y. And this is just something that you're going to have to memorize. There's just no way around it. You plug numbers or angles into the function and you get numerical values out. The sine corresponds to this side that's opposite, or the y value on the unit circle. Cosine corresponds to x, the x value. So that's why I wrote this that I have up here. Cosine t, comma, sine t is an ordered pair, thank you, that corresponds to x and y accordingly. Now, when I say SOHCAHTOA, that comes from the right triangle trigonometry. Sine of an angle is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent of an angle is opposite over adjacent. What SOHCAHTOA is it's an acronym for sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, tangent, opposite, adjacent. SOHCAHTOA. I've never heard the story. I've heard the acronym. That's why I say Google it on YouTube. Anyway, you can create a right triangle, and as long as you're looking at a unit circle, the radius of this circle is going to be 1. Okay, that's why we call it a unit circle. So the hypotenuse here will always be 1. Well, y over 1 is y. Well, that's the opposite, that's the side that's opposite the angle over the hypotenuse. So that's where the SOHCAHTOA comes from, and that will help you memorize what these trig functions are. Now, I do expect you to be able to find the exact value of the trig functions. You can use these definitions if you want to memorize this or use SOHCAHTOA. For example, look at example 1. It says find the values of sine, cosine, and tangent, cosecant, secant, and cotangent if this is a point on the unit circle. So here's a point, and it's on the unit circle, and it lies in quadrant 4. Quadrant 1, we start where both x and y are positive. Then we move in a counterclockwise direction counting our quadrants. Quadrant 2, x is negative, y is positive. Quadrant 3, x and y are both negative. And in quadrant 4, x is positive, y is negative. We'll look at the x value of this point. It's positive. The y value is negative. If we know the value of x and y, and we know that the radius is 1, we can either use SOHCAHTOA or we can use these special trig angles, trig functions, the definition of these trig functions based on the circular function, to figure out what sine and cosine and whatever of these angles are. Even though we don't know what t is, we know the points. Looking at these points, remember the x value corresponds to what trig function? Cosine. The y value corresponds to sine. If we're asked to find what sine of t is, sine t is going to be equal to negative 1/2. It's just the y value of this point. Cosine of t is the square root of 3 over 2. Tangent is y over x. Now, we can simplify this because this is a complex fraction by flipping the one on the bottom and multiplying by what's on top. So this is going to simplify into negative 1 over the square root of 3, which then we need to rationalize, and this is going to be the negative square root of 3 over 3. What we see here is these denominators are the same. They're just going to cancel out, giving me this. And then if you multiply this fraction by the square root of 3 over square root of 3, it's going to rationalize that denominator, meaning it's going to get the radical out of the denominator. So that's where we come up with this value. That's sine, cosine, and tangent. Now, if you will look here, cosecant is just the reciprocal, or we flip the sine. Or secant is the reciprocal of cosine. We just flip whatever we get for cosine. And then cotangent is the reciprocal, meaning flip the fraction here to get cotangent. So if I know sine, cosine, and tangent, I can then figure out cosecant. That's going to be negative 2 because the reciprocal of negative 1/2 is negative 2. Secant is going to be 2 square roots of 3 over 3 after I flip it and rationalize it. And then cotangent is negative square root of 3. So that's finding exact values of the trig function using a point that's on the unit circle. Secant, I just take the reciprocal of cosine. So there's some scratch work involved here that I didn't show. I'll go ahead and show that. The question was, how do I get secant from cosine? Well, secant is going to be the reciprocal of cosine, so that's going to be 2 divided by the square root of 3, which I then need to rationalize by multiplying this by the square root of 3 over the square root of 3. So that's where I ended up with 2 square roots of 3 over the square root of 3 times the square root of 3 is 3. No, there is not a button on the calculator for any of these functions on the bottom. There's only sine, cosine, and tangent. That's the inverse, and that's switching x and y. It's not the reciprocal. We're going to go into how to use the calculator to get approximate values too. But this right here was the scratch work for this problem. T is the angle. T corresponds to the arc length right here. If I were to flatten this curve, this straight line out around, wrap it around this circle, for example, if this were a string that was stretched tight, and I were to wrap it around a circle with a radius of 1, this arc length S is the distance that it would cover. Well, to this point, from the initial side, okay, let me back up a little more. The positive x-axis is called the initial side of an angle. And if we go around the circle where I stopped, this would measure that angle that's cut out here. This would measure that angle theta. So this angle right here, theta, corresponds to this distance, t. So the angle and the t are the same. The formula for finding arc length of a circle is S equals R theta. Well, S is the arc length, R is the radius of the circle, and in this problem, the radius of the circle is 1. So if we went all the way around the circle, what is the distance or the circumference all the way around a circle? 2 pi. Because the circumference of a circle is 2 pi r. Well, our radius is 1. It's 2 pi r, but our radius is 1. So I'm measuring this angle in radians, not degrees. Now this I'm assuming that you've heard before, but you may not have. We start with the initial side of the angle. Let me go to a lighter color. This right here is what we call the initial side. And this side right here then would be the terminal side of the angle. And that angle then would be theta, measured in radians. Starting out, we start out with 0 radians or 0 degrees, and then we go around a quarter of the way, and we're at pi over 2, because 1/4, because this is a quarter, these quadrant angles are a quarter of the circle. Well, 1/4 of 2 pi is going to be pi over 2. If we go halfway around, we're measuring at pi radians. If we go 3/4 of the way around, that's 3 pi over 2 radians. And then we back up at 2 pi, and we've gone around the unit circle one time. In degrees, this is going to correspond to 0 degrees and 360 degrees. This is 90 degrees, 180 degrees, 270 degrees, and then we're back at the 360. So that's, the quadrant angles, and they're measured in degrees and in radians. And then we have every measure in between. Now, we have some special angles, and I don't know if we're going to that yet. No, first we're going to find the exact values of the quadrant angles. So I'm going to write the quadrant angles back on this graph in terms of radians and degrees. So in radians, we're looking at 0 and 2 pi radians. We're looking at pi over 2, pi, 3 pi over 2. Does everybody understand why on a unit circle this is going to get us these particular angle values? All the way around the circle measures 2 pi r. Well, our r here, our radius is 1. How do I know? Because the distance from the center of the circle to the outside edge is 1. Now, if I were to measure this in degrees, we would be looking at 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then back to 360 degrees. So if you see an angle that doesn't have a degree symbol on it, you have to assume you're measuring in radians. So for example, if I asked you what is sine of 15, and I don't put a degree symbol on there, I mean 15 radians. Our angles here, if we go back to our definition of our trig functions, we were told that sine of t is equal to y, cosine of t is x, tangent of t is y over x, and then cosecant is 1 over y, secant is 1 over x, and cotangent is x over y. Looking at the quadrant angles, if I asked you to find sine of 0 radians, well, that's going to be the y value of this point, right? That y value is 0, so sine 0 is 0. Sine pi over 2 is what? 1. No. We put angles in, we get numerical values out. So now I've changed this angle to pi over 2. Pi over 2 terminates on the positive y-axis, right? Sine is the y value, so x is 0, y is 1. Sine of pi is 0, because once again, the y value of this point right here at pi radians is 0. Sine is the y value on the point. And then if we go around, we get sine of 3 pi over 2 is negative 1. 2 pi, we just terminate back where we started from. So this, you can see it's going to repeat. We can do the same thing for cosine. Cosine 0 is 1. Cosine pi over 2 is cosine pi, negative 1, and cosine 3 pi over 2. Now let's look at tangent. Tangent 0 is, it's y over x. So it's 0 over 1, and 0 over 1 is tangent pi over 2. It is undefined. Why is it undefined? 1 over 0 is undefined. Tangent pi is 0, and tangent 3 pi over 2 is... Notice here, this is just a little memory trick to help those of you who have never had trig before. Notice the s's and the c's go together. Sine goes with cosecant. Cosine goes with secant as far as the reciprocals go. And then the tangent and the cotangent are going to go together as far as the reciprocals go. So can you figure out, the other three trig functions based on this, looking at the reciprocals? What is cosecant of 0 going to be? Undefined, because the reciprocal of 0 is undefined. What is cosecant of pi over 2 going to be? 1. Cosecant of pi? Undefined. Cosecant of 3 pi over 2? Negative 1. You got the idea? Now, we need to talk about coterminal angles. And let me interject some space here. Coterminal angles have the same reference angle. I want to use this term reference angle, so I'm going to introduce it now. What it is it's the smallest angle that would be coterminal, the smallest acute angle that would be coterminal to wherever this angle would stop. So if we're looking at 7 pi, what it means is we always start out at the positive x-axis and we go around. There's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. 7 pi is coterminal to cosine pi. Does that make sense? It stops at the same place that cosine of pi would stop. So right here, when I ask you to find this value, this is coterminal to cosine pi. And look at this quadrant angle. What is cosine pi? Negative 1. Try your best, and it's hard in a pre-calc course as opposed to a trig course, but try to not translate radians to degrees. Try to become fluent in radians. When you become fluent in a second language, you no longer have to translate back to your primary language. You just think in that language. I want you to become fluent in the language of radians. I don't want you to be translating back and forth, because radians make so much sense. And I'll try and delve more into why they make sense as we go through more examples. So cosine pi, remember, is the y value. And looking back up here at the graph that I was drawing on for cosine 7 pi, cosine is the x value. And the x value here is negative 1. So cosine of pi will be negative 1. Cosecant 11 pi over 2. We've got to find out what is that coterminal to. So cosecant 11 pi over 2 is going to be coterminal. Now 11 halves is 5.5, right? So we're going to go around 5 times, which is an odd number. It's going to put us over here. And then another half. So that's going to be coterminal to 3 pi over 2. And cosecant of 3 pi over 2. Cosecant is the reciprocal of sine. Sine of 3 pi over 2 is, so this is going to be negative 1. Okay, this is just the angle, the 7 pi. So going back, I was looking at this circle up here, the unit circle that we were given, and counting the radians, 7 pi, we got to go around the circle until we've gone 7 pi times. So we start out always at the initial side, and then we go around. There's 1 pi, because we're right here at pi, right? And then you go around, there's 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi stops right here. Well, that angle is coterminal then to this angle right here, which measures pi radian. So that's why I said cosine 7 pi is coterminal to cosine pi. There's a theorem you're missing. and I need to tell it to you, the coterminal angle theorem. The value of a trig function at an angle will be the same for every coterminal angle. 11 halves. Okay, 11 divided by 2 is 5.5. So there's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and then a half of a pi. Because the quadrant angles are measured in increments of a half of a pi. Consequently, this is one of the reasons I like radians. You can deal with the fractions, the numbers only, and then just stick the pi on there. So you can use your calculator to simplify fractions, and then just stick the pi on there whenever you're done. As you have questions, please ask them. The next thing I want to mention is the exact value of special angles. There's certain angles that we consider special angles, and these angles are all of the quadrant angles that we just went over, and multiples of 30 degrees, 45 degrees, and 60 degrees. And these will be our reference angles. I'm so glad you asked. In radians, this would be pi over 6, pi over 4, and pi over 3. Beautiful. Notice right here that pi is equivalent to 180 degrees. Right? And things that are equal, you can put one over the other, and you have a value of a fraction that is 1. So what I can do here is how we ended up with these measures in radians and degrees is we start with an angle that's in degrees. And we multiply it by, I want to convert from degrees, so I want the 180 degrees on the bottom so that the degrees will cancel out, to radians. And 180 degrees is equal in value to pi radians, right? So 30 over 180 will reduce to 1/6. So that's where the 1 pi over 6 came from. And now your measure is in radians because the degrees canceled out. You may or may not have seen that before, but it works beautifully, and it works every time. And we can go from radians to degrees. Yeah, you just flip it. So let's say that I wanted to go from, we'll do 7 pi over 6. This is measured in radians, right? If I want to convert that from radians to degrees, I'm going to put the 180 degrees on top and then put the pi on bottom. Now the pi's are going to cancel out, and 6 goes into 180 30 times, so this would end up being 210 degrees. Get with me if you need help with this. For the special angles, we're going to make a chart, because basically if you know sine and cosine, you can figure out everything else. So the angles I'm going to put across the top are special angles, and I'm going to start with the quadrant angle 0, and then we're going to go to pi over 6, the smallest special angle, pi over 4, pi over 3, and then we end up at the first quadrant angle. That's the positive y-axis, and that would be pi over 2. So we're going to do sine of these angles and cosine of these angles. Because if you look at our unit circle definition up here, everything's in terms of either x or y, isn't it? Which means all of your trig functions can be written in terms of sine and cosine. So if you know sine and cosine, you're in business. So we're just going to fill in this table. Now, I'm going to show you a trick on how I learned how to fill in this table. It works if we put everything over 2, and everything on top is going to be a square root. And we're going to count from 0 to 4 across here. So this becomes the square root of 0, the square root of 1, the square root of 2, square root of 3, square root of 4. And then along the bottom, go back the other direction. Square root of 0, square root of 1, square root of 2, square root of 3, square root of 4. Simplify what we have now. What is the square root of 0? It's 0. So sine of 0 is 0. Pi over 6, what is the square root of 1? So that's what sine of pi over 6 is. Pi over 4 is going to be the square root of 2 over 2. Can't simplify that. Pi over 3 is going to be the square root of 3 over 2. That doesn't simplify. What is the square root of 4? And 2 over 2 is 1. And then you do the same thing going back. You just simplify. And this is how you can make a table with all of the exact values of all of your trig functions. Well, sine and cosine. And knowing those values, you can get every other trig function. I'm not going to give you a unit circle. I expect you to know what these exact values of the special angles are. Now, if I put this information together with the signs of the trig functions, and I know I have it in my notes somewhere, but if I put that together with the signs of the trig functions, let me go ahead and mention that now. In quadrant 1, all of the trig functions are positive. In quadrant 2, sine and its reciprocal cosecant are positive. Tangent and its reciprocal cotangent are positive. Cosine and its reciprocal secant are positive. And if you will remember, all students take calculus. You can remember the signs of the trig functions. So in quadrant 1, all trig functions are positive. In quadrant 2, we have sine and its reciprocal cosecant. In quadrant 3, tangent and its reciprocal cotangent. And in quadrant 4, cosine and its reciprocal secant are positive. So if we know the reference angle, which is the acute angle that's made with the coterminal side of an angle and the x-axis, we know what quadrant it terminates in. We know the special angle, the reference angle is going to be, if it's one of the special angles, we can find the exact value of any of the 6 trig functions in any of the 4 quadrants, as long as the denominator measured in radians is either 2, 3, 4, or 6. In example 4, we're asked to find the exact value of sine 30 minus cosine 45. Looking at the table that you have in your notes, this table right here, what is sine 30? 1/2. And what is cosine 45? So this is going to be 1/2 minus the square root of 2 over 2. Notice that we have common denominators here, so we can combine these into one term, 1 minus the square root of 2 all over 2. And that's the exact value of sine 30 minus cosine 45. What is sine 3 pi over 2? Remember, that's the quadrant angle, because the denominator is 2, that terminates on which axis? X or Y, positive or negative? Y negative. So if we've got our little Cartesian coordinate system here, 3 pi over 2 will terminate right here, so that this is 3 pi over 2. And sine is the y value of the point, so that's going to be -1 plus, and what's tangent of pi? Pi is the negative x-axis. Tangent is y over x, so that's 0 over -1. So this answer here, when we combine these two terms, is going to be -1. This is just reasoning it through. Next we have secant of 30. Secant is the reciprocal of what trig function? Cosine. So we look up here at cosine of 30, which is pi over 6, and we get 2 over the square root of 3 is what it would be, right? I look at the reciprocal of square root of 3 over 2, I get 2 over the square root of 3. And cotangent of 45 is 1, because the value at 45 degrees of sine and cosine is the same, so it's cosine over sine, that's going to be 1. I need to rationalize this denominator, and when I do that, what am I going to get? And that's your final answer here. So let me go ahead and write these above here in degrees. This would be 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and your quadrant angles are going to be 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, because 360 degrees takes you all the way around the circle and back to where you started from. All right, now, Nick, you asked the question about the calculator. How do we handle the calculator if we don't have a sine, cosine, or tangent? Well, cosine 48 degrees we can do on our calculator, which means I should have had my calculator open already. First thing you want to do is make sure your calculator is in degree mode. And we will be flipping back and forth between radian mode and degree mode. Does everybody know where the mode button is on their calculator? It's next to the second. Make sure it's in degrees, because A here asks us what cosine of 48 degrees is. So we're going to go to mode. Mine is in radians right now. I figured it was, because that's what we use more often than not in calculus. and we want to go to degree mode, hit enter. It's a toggle, so it's taken, and then I'm going to hit second quit to get out of the mode function. So then I'm going to hit cosine of 48. Now, if you want to keep your calculator in Radian mode all the time, let me show you what you can do. Because radian's the good default, because most of what we do is going to need the calculator in radians. You can still do cosine 48 degrees. It's just that you're going to have to hit cosine 48, and then you see the button that says angle right here that's right above the apps key. Hit second angle, and the number 1 is the degree symbol. And now it's going to give us the cosine of 48 degrees. Notice this is different from just cosine 48, where 48 is 48 radians. So if your calculator's in degree mode, you just hit 48. But if your calculator's in radian mode, cosine 48 is going to give you cosine of 48 radians. You can always make sure you get the right thing by sticking the degree symbol into the calculator, even if it stays in radian mode. So that's kind of cool. So if we were going to round this to how many decimal places? 2 decimal places, what would we put? 0.67. So this would be 0.67. We have cosecant 21 degrees, but we said for B here, we don't have a cosecant button on our calculator, but cosecant 21 degrees is equal to 1 over sine of 21 degrees. So on our calculator, we're going to hit 1 divided by sine of 21 degrees. And I think I put my calculator in radians, so I'm going to have to stick that degree back on there. And we get 2.79. And then tangent. Now our calculator's in radian mode, so we're okay with this. We're just ready to hit tangent. And we put in pi divided by 12. Use the actual pi button on your calculator, which is located right here, but you have to hit shift to access it. Divided by 12. And you just type it in exactly like you see it, and you get 0.27. Alright, well what if the radius is not r? Is not 1. What if the radius is some positive value? Radius, by the way, will always have to be positive, because remember, with any circle, the equation of the circle, if it's centered at 0, 0, is x squared plus y squared equals r squared. The radius is a distance. It's always going to be positive. Only the x and y will be negative. So we're going to use these trig functions. Just get y over r over y. Just replace the ones that you had in the original definition of the trig functions. Replace the ones with r's. So in example 6, we're asked to find the exact value of each of the 6 trig functions of a positive angle theta if this point is a point on the terminal side of the angle. So what we're going to do here is I'm going to go ahead and plot this point. It's at 4, -3. So that's 4 along the positive x-axis, -3 along the y-axis. So there's 1, 2, 3, 4, -1, 2, 3. That's this point right here. So we're looking at a circle where the radius is going to be this distance right here. This is r. Can we figure out what r is if I know that this point is at 4, -3? We can use x squared plus y squared equals r squared, right? So x is 4, y is -3. So I get 25 is equal to r squared. Well, that's 16 plus 9. So r is equal to 5, because 16 plus 9 is 25, and the square root of 25 is 5. So using these definitions of the functions here, or you could drop a perpendicular here and use this angle right here, the reference angle, and you know that this side right here opposite is -3, this side is 4, and you can use SOHCAHTOA. Sine of that angle is going to be opposite over hypotenuse, -3/5. Cosine is 4/5. Tangent, -3/4. And if you know cosecant, secant, and cotangent are reciprocals, we can find these rather easily. Cosecant is -5/3. Secant is 5/4, and cotangent is -4/3. I don't know what the angle is, and I wasn't asked to find the angle. I was just told that it was going to be an angle so that this point was on the circle. I didn't need to know what the angle was, but yes, I would have to do the inverse trig function if I were to find the angle.